We'll have 3 talks before coffee. And the first talk will be given by Dmitry Ponomarev on spectral theory of convolution operators.
Thank you very much, Martin. First of all, I'd like to thank organizers for putting together all this wonderful conference. For me, it's amazing to meet all the people whose name I know from the papers, but I've never met before. And a special thanks goes to Gennady Mishuris, who made extraordinary effort to bring me here all the way from Vienna through a berry street. And well, thank you, Gennady. So again, before I start, so I come from Vienna, and I don't know anyone in Vienna or in Austria in general who is doing Wiener-Hopf. However, there is some connection. So here you can see the library, Technical University of Vienna library. If you go there, you can dig for the book, famous Muskilashvili book on singular integral equation. And then if you look who was translating this book, is someone named Rainer Radok. And this man is quite a remarkable story, and he spent most of his life in Australia. And but before he became important applied mathematician there, he was interested in translating books, and he spent some time in Vienna as well. And he's mathematically genealogically related to our research group in Vienna. So there is some connection with with Wiener-Hopf I'm working on. And well, this connection was pointed out by my colleague Franz Leitner. And well, there is another connection which is yet to be explored. If you look at the on the roof of this library, well, guess who are the creatures? Well, these are all owls. So I don't know the precise nature of this connection. Perhaps this library is supposed to be a silent place, so that's they should somehow do the noise reduction. All right, so finally I start with the main content. So the main object of my studies is convolution equation, as in many other cases, but on an interval. So consider Fredholm convolution equation. This form, so given kernel function k and in general non-homogeneous term g and some constant mu, we want to find f. And I want to give some provide some apology for considering such a problem, because it may here mainly people consider problem on the half line, on system of equations on the half line, which arise in different diffraction settings and so on. But equation on the finite interval have a lot of applications as well, and you may argue that applications are not so numerous, but my counter-argument would be that it's actually the first convolution equation that I encounter, and that's how I trying to figure out how to solve it. I learned about Wiener-Hopf and a lot of other things. So this, well, of course you can say maybe I'm an extremely unlucky person to start with such problems. So applications range from electrostatics, fluid dynamics, quantum mechanical, some one-dimensional quantum mechanical problems, all the way to probability theory, some problems in the signal processing and approximation theory. And to be even more convincing, consider, for example, equation with very simple kernel, which is like 1 over x squared plus 1. And this equation alone arises in most of those contexts that I mentioned on the previous slide. So typically in electrostatics problem with circular symmetry, and then had circular condenser capacity problem is reduced to this. Similarly for calculation on of torque on the circular plates rotating in a viscous fluid. Then there are some 1D models of interacting with delta potential systems in quantum mechanics, and it's known, and depending on the context and different value of mu and g, it's known under different names, and it doesn't have a closed form solution, so people try to extract some asymptotical behavior. And I find this very annoying that such simple equation of such simple form do not admit closed form solution when you restrict problem to interval. So I try to make some contribution to see what can be done in a constructive viewpoint. So. Well, if you look at the timeline, so it's, for example, this equation, the earliest paper I could trace is from 1923, and it's the famous people like Craig Tracy and Harold Widom still continue working on such things asymptotically. So this is just to say that this convolution equation of the interval are important. And to give another application which is like very concrete and understandable for everyone, I guess. So we consider so-called geological prospecting problem. So this is Fredholm equation of the first kind. So the problem here is to invert this integral operator. Given the right-hand side, we want to compute rho. So the context is the following. Suppose you have half space, and you locally Earth, let's say, and and in some depth h from the surface there is an anomalous gravitational region with density rho. So, and then you do the measurements exactly above this region, and you measure the force, the gravitational force produced by this region. So, first, this force, for example, at point x, it will be all the forces that act at this point from all the points from this region. So that's how by summing them or integrating them you get this guy. And why is it exactly this form? Because the gravitational force is well, it's a gradient of Newton potential, so it's inversely proportional to square of distance. Square of distance is clear geometrically what it is, and then somehow you measure only vertical component of this force. So you have to multiply by cosine of this angle, which gives you another half power of this. So that's kernel that can be explained in 3 minutes, and given f, this measurements we want to find rho. Okay, so enough with applications. Let's set up the stage. So integral operator I will denote by this letter fracture k. The interval I will take to be symmetric from minus AA, but of course everything is translation invariant, so you can take it as a 0 to 2A, for example, the subset of positive half-line. But for convenience, that will be clear later, I will take symmetric interval and assume the kernel is kernel function is real valued and even. So this subscript r means that it's real valued. And then instead of considering this equation, it is sufficient to consider homogeneous version of this equation. And why is it so? Well, because homogeneous version provides solution of homogeneous problem, provides the spectral resolution of the operator, and then if you know all the eigenfunctions, eigenvalues, you can construct resolvent of this operator and solve it for any mu and g. So without loss of generality, we can consider homogeneous problem, which is a spectral problem for this equation. And note also that if, for example, mu is equals 0, so we have first kind equation, equation of first kind, like on the previous slide that I showed. So the problem of inversion of compact operator is ill-posed, and if you construct, you need to regularize it, and if you construct an inverse in terms of expansion of the over the eigenfunctions, and you truncate this expansion after the finite number of terms, then you get regularization of this problem. So this is not so silly way of solving the problem. So to make things more precisely about the eigenfunctions, so operator which I call fracture K is compact, because we assume kernel to be sufficiently regular, so we can say it's Hilbert-Schmidt, and so compact, and it's even, kernel function is even and the real value. That means that operator is self-adjoint, and then we can readily apply spectral theorem, which tells us that there exists a discrete set of eigenvalues lambda tending to 0, and corresponding, so these are eigenvalues, and corresponding eigenfunctions f of n will be mutually orthogonal, and they will form a basis in the range of this operator, integral operator. This is all very general stuff, so it's not so useful for the moment. So let's make a little bit of more assumptions to say more about the structure of the spectrum. So suppose that the kernel is positive definite. So positive definiteness means that you have this inequality. So you essentially act the integral operator with some arbitrary phi in L2, and you integrate against the same phi again, and the result should be positive. And alternatively speaking, this means that Fourier transform of the kernel is positive. You can get it by applying Plancherel theorem here. So this is first assumption, that positive definiteness of the kernel that we will need. And second assumption is that I assume that the kernel Fourier transform of the kernel is of this form. So it's decaying away from the decaying with the distance from the origin strictly monotonically. So it has some maximum at the origin, and then it decays somehow. And of course it's symmetric, so because it's even function. So this is the Fourier transform of K. So this is the typical shape of the kernel that we will consider. But in most applications that I show the kernel are like this. So under these two assumptions, what we have is that spectrum is simple. So for each eigenvalue, there is only one eigenfunction. This will be very important, and also we can, by trivial computation, we can show that lambda is between 0 and k hat of 0. So it's essentially by Plancherel theorem. To prove spectral simplicity, I won't give you the complete proof, but I will show you the main ingredient of the proof, which I called energy identity. And similarly to ODs and PDs, where you have energy balance on the form that you bound your solutions in terms of initial boundary data, here you can also prove something similar. So you can bound Fourier transform of each eigenfunction in terms of the values at the endpoints. So in particular, what it tells us is that if eigenfunction vanish at the endpoint, then it should be vanish identically. So they cannot vanish at the endpoints. at both endpoints. And from there you can deduce simplicity of the spectrum. You can and from simplicity you can deduce a lot of things. So this is this identity is very important. Okay, so in particular it implies that all eigenfunctions are necessarily even or odd. So it's the commutation with parity operator, the original integral operator, is obvious, but it's not clear if every eigenfunction is of specific parity. Well, simplicity of the spectrum guarantees us that, and all eigenfunctions can be chosen to be real valued. These are all very qualitative stuff. But how do we actually find eigenfunctions? So and here's there are lots of works on a kernel of very specific type, which typically where Fourier transform of a kernel is a rational function, and well, in the original domain you can also solve the problem if the kernel is somewhat very simple, like combination of trigonometric functions or exponentials, polynomial times exponential, or just polynomial. So very elementary functions. There are some more exotic methods, like for example Latta's method, where when kernel satisfies some linear differential equation, then you can also reduce problem to ODE essentially, but nothing more general seems to exist. And so how those eigenfunctions actually look, and well, also to at this point to kind of give you an idea of the difficulty of the problem, and on one hand show you the structural simplicity of the solution. On the other hand, paraphrase here the paper of Leonard and Mulikin, which consider some specific kernels which are very common in the origin of Wiener-Hopf theory. So this essentially the Laplace transform of something, and under the assumption of such form of the kernel, they managed to show that eigenfunctions are essentially cosines and sines, well, shifted by some constant, and this is this is very interesting, because in general the convolution equation is convolution equation on an interval is equivalent to the solving such problem is equivalent to factorization of triangular matrix function with exponential factors. And we've heard from talks of Frank and Ilya that such problems are very difficult. So perhaps at this point I should write down this connection. So we have our equation. On the interval minus AA, and you extend it to the whole line. So first of all, you denote f0 the extension of f by 0 outside of the interval. So this is characteristic function of interval. And then you extend the equation to the whole line. So you have here you have first of all you have equation on the whole line, because f is supported on the interval. And then, because we extend the equation to the whole line, we have to add something so it would be valid on the whole line. And this this something should have the following form. So it should be something that is vanishing inside the interval, but non-vanishing in the exterior. So, and exterior is the complement of two half lines. So then you can convince yourself that the form of this extension function should be like this, and this is already valid on the whole real line. So it's here we assume that f, for simplicity, we take f to be a even function. So it's either even or odd. So suppose it's even. So then we have a complement of the complementary part psi here, which is symmetric on the right of the interval, on the right half line to the interval, and on the left. So it's essentially given in terms of one half line unknown function. And then if you do the Fourier transform,
Sorry to ask.
Yeah.
In which way you extend to the kernel?
Kernel I extend in kernel has to be defined first of all on the double size of the interval, right? Because it depends on the difference of two arguments. So here I use suppose that kernel is given as on the interval as a restriction of some function on the whole line. So then I extend it on the natural way, right? So, and this would be important. This would be important when because I will consider a large interval. So in this case, I won't be able to extend it like the way I want. So it will be somehow I would need kernel to be defined on the whole line in order to consider the asymptotic of the large interval. But I will come to this.
But you see, if you have the kernel only on your interval, then the equation you write down now depends on the way how you
yes, it does. Yes, yes,
kernel.
Yes, it does.
These are the set of
yes, yes, it does. It does.
And
it does.
Maybe it has different nature in this case.
Yes, of course. This is another problem that I will mention at the end for a fixed interval, which we don't try to enlarge asymptotically. What is the beneficial way of extending the kernel in order to say something to be in a more solvable class, let's say. So so here it's kernel is extended somehow on the whole line. And then if you take Fourier transform, you have convolution becomes a product. And well, here I should say that psi, which enters here, the support of psi is a positive real line. So so you have things like that. Then you have exponential factors because of shifts. And similarly here. Not sure if it's visible. Yeah. So, and then because f hat times times 2 pi I a k is a plus function, and psi k is minus function. We can write this as a matricial problem for the vector psi k and f hat then what it would be? Well, have we multiply this by e to the minus 2 pi I k, and here we have psi minus k vector, which is analytic in the lower half plane, and similarly we have things like that, which is also analytic in the lower half plane, and then you have e to the minus 4 pi I k, perhaps with minus sign, and and here you have k hat k minus lambda. Here you have 0, and here you have exponent with positive 4 pi I k. So it's triangular matrix. Kernel enters in only here, and but the nasty things are these exponential factors. And well, let's keep this in mind. So on one hand we have this, we heard all the difficulties related to factorization on this matrix, and on the other hand we have this result by Leonard Mulikin that the spectral is essentially eigenfunctions are essentially cosine and sine. Well, what they don't tell, or they don't tell explicitly, is what are the frequencies. So what are the eigenvalues. So, and those are given in terms of solution of some auxiliary problems which are not available in a closed form. But still, the form of the eigenfunctions for this type of kernels is like this. It's very simple. So, okay, there are in constructive way there are different approaches how people attack this this problem, and all of them can be put into few categories, which I roughly try to do here with no hope to be complete, of course. So either some external term, forcing term, is introduced, so the problem is considered in a non-homogeneous form, and then the analyticity of this, or the structure of the solution for this non-homogeneous term is studied, and somehow a structure of general solution can be deduced. Or there are some extra parameters that are introduced, like the size of the interval, and then by establishing some differential relation with the with respect to this parameter, we can reduce the problem to the system of differential equations were highly nonlinear and with no hope for the analytical solution. This is the content of so-called embedding method. And well, I normally added here the fourth point, mentioning the work of Frank and Ilya and Christina, but somehow this is the old version of my presentation. So okay, so this approach, none of this approach, as far as I know, give explicit form of the eigenfunction. So to simplify things, to try to be able to say more, let's consider the case when the interval size is large. So this is interesting case because the operator loses the compactness. So it's interesting also to study from function theoretical viewpoint. And here there are a number of works regarding distribution of eigenvalues as the size of the interval increase. So the first eigenvalue can be sandwiched between some bounds which would tend to k hat of 0, and this is rather easy to show. And then you can quantify these results, and this involves much more work, and this is done by Wiedem. And but this is so the eigenvalues are written as expansion over the some inverse powers of the size of the interval. So you kind of approximate them as the interval goes large. And this type of expansions heavily depend on the regularity of the Fourier transform of the kernel at the origin. So what type of smoothness you have here at this point. And there is Widham's result is very important, but it assumes that the kernel is has a second derivative here, which is not the case for the kernels that I showed you before. They have a peak here, so the discontinuity in the first derivative. So these results do not apply. And also one can study a distribution of the eigenvalues for any size of the interval. So essentially, it can be shown that the eigenvalues are roughly asymptotically. They are roughly the samples of the kernel function for this space. And finally, what about eigenfunctions? So at the end, we wanted to solve something, right? So there are three important papers. Well, there are much more, but this I believe are the most important from my point of view. And they try to write the eigenfunctions in terms of the in terms of explicit expressions. And here, the form of eigenfunction captures this trigonometric behavior, and plus some other term more complicated, and but essentially it's like the perturbation of trigonometric functions. And all this work is done for the under assumption that initial kernel decays at infinity fast enough. So equivalently speaking, that we need here at least C2 smoothness at the origin of the kernel function. But again, those kernels that I showed you in the very beginning in the applications, they decay like 1 over x squared or 1 over x absolute value of x to the power 3. This cannot be done, and so their constructive approach cannot be extended to treat such cases. And yes, so the last important work here was by Joseph Keller and Charles Knessel, and they somehow didn't impose restriction of exponential decay of the kernel, but they assumed the finiteness of at least few first moments, which again is not the case for this simple kernel. But still, their work is very important. And so, in our approach, we assume that kernel is even real valued, as I said. We assume that it's C1. And since we consider asymptotics on a large interval asymptotics, we talk about we define kernel on the whole real line. So that's relevant to the question of Sergei. So it's it decays as a one function. Essentially, should decay. Positivity, positive definiteness, and this assumption that I explained essentially. Decays strictly monotonically from the origin. We make no assumptions on the analytic structure of the Fourier transform of the kernel in the convex plane at all. So all the assumptions are on the real line. So the result can be formulated for the eigenvalues in the following form. So we define well, k hat is a Fourier transform. Then we define this function g, which is, by the way, regular on the real line, so it's no singularity here. Define x plus in terms of G. H, calligraphic H is a Hilbert transform. Then eigenvalues can be found approximately from solution of the set of algebraic transcendental equations. And it might look a bit scary, this slide, but let's consider just this first set equation. So first set of equation is for even eigenvalues, the second for odd eigenvalues. So consider the first one, so even part of the spectrum. So on the left-hand side here, we see that it's some function of kappa. It might be complicated because of this Hilbert transforms and so on, but overall it's just some growing function of kappa. And on the right-hand side, we have constant, so just horizontal line, or set of constants if we consider different m. So, for example, for m equal 1, we have the solution will be this point. So this will be the kappa 1, and for the next equation, we will draw the next next multiple of pi. It will be 2, and so on. So, and then if you evaluate your the k hat at this point, you will get approximation to eigenvalues. So, similarly for the odd part. For the eigenfunctions, we can show that it's once we know those eigenvalues, we can show, for example, the even eigenfunctions are can be written asymptotically like this. So it's essentially cosine, the good trigonometric function as we expected. Well, with maybe some messy constant, and then there is some integral term, which is a little bit messy, but well, it's there. And well, and some residual term which goes to 0 as the interval grows. And similarly for odd eigenfunctions. So essentially they are given explicitly. So these are signs plus some more messy functions. So how to get this? Of course, I have no chance to show you the complete proof. I will just illustrate the steps, the main steps. So we reduce the problem from the half line, from the interval to the complement of the interval, which consists of two half lines, and then using parity, we put everything on one half line, which is let's say the right half line. So here. This problem we can approximately solve, and from the solution of this problem, we reconstruct solution inside of the interval. So this is the strategy. And then because we did continuous extension, the solution on the half line should match the solution of the interval at the end point. And this matching, this continuity will enforce condition on lambda on the eigenvalues, and this will get us the characteristic equations that I showed you on the previous slide. So this is the connection between solution on the interval and on the half line. So f is inside the interval can be defined in terms of continuation of the eigenfunction to outside of the interval, which is done from the original equation itself. So that's we continue f from the validity of the equation itself, and then we get f from the exterior, and then it turns out that they have to be related in such way. So plus and minus here means that plus is even functions, minus or odd functions, and so the kernel here is this guy. So not so messy, but not so piece of cake. Denote this by T, this guy. It's an integral part of this kernel. And then, what about the half-line problem? The half-line problem can be formulated as the equation of the half-line with two kernels. Convolution kernel, this is a good kernel, Wiener-Hopf kernel that we are happy with. And then there is a second part, a kind of Hankel kernel or cross-correlation kernel, which depends on the sum of the arguments, and well, there's also a. So this comes from so we formulate the problem here, and this part contributes exactly in the form of this term. And but this equation on a half-line, so it's already simple and interval. And also there is this extra term which can be written in a convolution form, but the kernel will be discontinuous. But that's not a problem. We can eliminate it. Now, in order to solve this problem on the half-line, we observe that this T is actually decaying for large argument. So, and x and t are both positive here, and so the equation is for phi, which is a shifted version of f. So I consider f x greater than a, and I just denote shifted version by phi, so to consider it on a positive real line. The argument is always positive here, and as a is large, this term is negligible because its decay is related to the decay of the original kernel. It can be shown. And so once we throw away this guy, we can solve the half-line problem. Okay, it's integro-differential problem, but we can still solve it with Riemann, reduction to Riemann problem. And so it has a very simple solution, like this, in terms of x plus and g, similarly to what was introduced before. Because of the differential operator, it depends on the constant. This constant is f of a. Now we plug this. Remember the first lemma that I showed that connects solution on the interval with the half-line. We plug it there. So now we have the solution on the half-line. We plug it there and reconstruct solution inside the interval. Then we can do some simplification, and eventually we arrive at the solution inside the interval in this form. So it's here we recognize that there will be something that will form cosine and sine depending on the parity that we choose, and then there will be this messy integral term. And now to find eigenvalues, we just need to match it at evaluate it at x equal a, and so this f of a would just cancel out from everywhere, and we'll have some equation for k0, and k0 is essentially lambda in these guys. So it's k0 is so suppose lambda is here, and the value of k, for which k hat of k would give us lambda, is exactly k0. So this is how we introduce k0. So it's once we know k0, we know lambda. Okay. We can, so this is one way of deriving this characteristic equation for the eigenvalues, but there is, of course, there will be this integral term that is messy, and x plus is in the integral form as well. So it will be a rather unwieldy expression, and we can do something smarter. We can observe that for large a, this integral is highly oscillatory. So actually, if you consider the if you consider your solution somewhere inside the interval, like close to the origin, those exponents will be like a, or of the order of a, and so integral is oscillatory, and then the integrand is regular, so there is no singularity here. The singularity of here is the same as here, so everything is regular, and the whole integral term is asymptotically, the leading order is 0, so this is the dominant term. But on the other hand, we know that eigenfunctions should be real, so that means that this guy should be real, and this real valuedness requirement gives us much more simple form of the characteristic equation determining numbers. So now I will say a couple of words about what to do when the interval is small. So of course, this is from theoretical point of view, it's much less interesting situation, because if you have regular kernel and interval is small, then you would naturally want to, okay, this here we rescaled everything to -1 to 1, and you naturally want to expand this into a sort of Taylor series, and then you have you can solve things explicitly. But what happens is that when you do such expansion, well, it's fine, it works, but you approximate your original operator with an operator of a finite rank. So the operator whose range is finite dimensional, and your dimension depends on how many terms of expansion you take in of your kernel function. And so if you're interested in a spectral structure and you want to capture something interesting, you need to take actually a lot of these terms in the expansion. So then you have to solve big matrix problem, and on the other hand, this might be numerically challenging, because for regular kernels for which we can do such expansions, we can show that eigenvalues actually decay geometrically. So there will be very small eigenvalues. So, and if you have to solve a very large system which is ill conditioned, that may not be the best thing to do. So why not to try to do something different? So instead of fitting the kernel with some classical family like monomials or Fourier basis, exponentials, let's try just to choose a family of kernels for which we can solve in some sense the equation, and then see how close the kernel is to the solvable family. So, but as I said, on the interval, not so many kernels are solvable, and one exceptional kernel is kernel of this type, and this kernel arises in signal processing. In many contexts, it's functions which are band and time limited. They are eigenvalues of this kernel, and so there's been a lot of studies on this. And the important feature of this kernel that it's integral operator with such kernel admits commuting differential operator. And because spectrum is simple, that means that we reduce the original problem of the integral equation to some ODE problem. So we just need to solve a differential equation. So the kernel is like this. So why not to approximate the original kernel with something from this family? Of course, we have only 2 parameters, so we have a big limitation. But it turns out that it's still surprisingly it works quite well. So, for example, often you have in applications the kernels which are of bump type. So essentially the shape like this, like Gaussian, or 1 over 1 plus x squared. So it's this type of kernel, which are called bump kernels, they can be approximated by Sage kernel, and so 1 over hyperbolic cosine. And Sage kernel belongs to this family, and so we get OD, and then for we can approximate, can do some approximation further. So first of all, we can reduce the problem to the kernel with this meromorphic function Sage, and then the solutions are solutions of ODE because of commutation. So and this ODE is well-known ODE. It gives ODE for special functions which are prolate spheroidal wave functions. So actually we don't need to solve anything. It's just you just need to take some functions which are already coded. So then you do this, you plug it back in the original equation, you get lambda if you want to compute lambda, but normally we're interested in eigenfunctions themselves. So that's just an example of how we can approximate a kernel in a non-orthodox way, let's say. So let's show numerically how things work. So we focus on a particular kernel on, that I showed in application of geological prospecting inverse problem. So this kernel can be shown to satisfy our assumption. So it's positive definite, Fourier transform is positive, strictly decaying probably from the origin. And well, what about eigenvalues? So remember we have to solve this set of equations here, and the picture here is what I tried to illustrate here. So we blue curve is the left-hand side of this equation, is a function of kappa. So it turns out that it's essentially linear. And the horizontal lines, parallel horizontal lines, are the multiples of pi. So we look at the intersection. So at this point, for example, this would give us first eigenvalue, and the next point, second even eigenvalue, eigenvalue corresponding for even eigenfunction, and so on. And vertical lines here are actually numerical solution, like of the original equation itself. And we see that the intersection of blue curve with horizontal line occurs exactly at where the vertical lines are. Well, for many first eigenvalues, well, then it starts to diverge, but I don't know if it's numerical or asymptotical error. So but these are even eigenvalues. Even what eigenvalues they interlace. So here it means that you can maybe get like 30 approximation of 30 eigenvalues and eigenfunctions, and if they decay geometrically for all the applications, this is very good approximation of the spectrum. Similarly for the odd part, just everything horizontal lines are shifted by half. And that's how eigenfunctions look. So I compare again numerical and asymptotical solution. So for example, third eigenfunction, which is the second even one. Fourth. And if you go, for example, to 24th, then you see that actually, okay, there's like trigonometric behavior, but then near the endpoints, there are something which is essentially non-trigonometric. And this is the one that is integral term kicks in. So I did the same for example, for another kernel, for which I had to work on numerics more, and yeah, we see that this is not an artifact or something. So it's exactly the numerical and asymptotic solution. It's their correct behavior. It's not purely trigonometric. What about small interval? Well, that's this kernel is also this bump type, so we can approximate by Sech kernel, which gives us this prolate spheroidal wave functions, and this is, for example, third eigenfunction, fourth eigenfunction, well, not trigonometric at all, by the way. So, but we're still with this Sturm-Liouville property. And well, to sum up, just to say that this essentially what I've done is that extending the work of by different methods, the work of Hudson and Kneissl-Keller for kernels which allow which allow decay, non-rapid decay. So Hudson assumed that kernels are exponentially decaying, which is a very strong assumption. And Kneissl-Keller they didn't do rigorous mathematical analysis, but they did some calculation. In their calculations, the moments of the kernel arise, and clearly that the moments of the kernel will be infinite if the kernel is not decaying fast enough. So that's for this 1/1 plus f square kernel, for example, is not applicable. The quantities blow up with enter this paper. So I wanted to extend this, and this was the result. And for the small interval case, I kind of gave this result for the completeness, and I think this is an interesting idea to approximate something with like from a more narrow family, but which somehow fits the original operator better, because it's the approximate original compact operator with another compact operator, which is not a finite rank, so but still close to the original one. So it should somehow provide better approximation, and it does in this case. And well, there are still a number of things to work on. So the error analysis can be made more rigorous. So there's some estimate that I still don't have, and we can simplify this equation for the for eigenvalues. We see that it's nearly linear. So, but it's analytically, it's not easy to see this, and we can tighten the assumption of the kernel. Can consider kernels without this monotone decay, and then of course we can also try to improve the accuracy. When A is not large, we can do the iteration, solve the problem on the half line, compute solution inside the interval, then again solve on the half line. Compute solution inside the interval, because we have these integral formulas. So once we know one solution, we can iterate and get something better. And similar results. I wonder how this connects to the results on large finite chocolate matrices, which are essentially samples of the continuous integral equation. And I know that, for example, some people like Sergei Grutsky, they work on this, and they get similar results for the eigenvalues, similar to the equation. And with this, I thank everyone.
Thank you very much. Thank you. So we have time for a couple of questions, please.
You considered all this equation in L2 spaces.
Yes, yes.
And the kernels in L2 and L1 mainly. So from the viewpoint of elliptic boundary value problems, which is the origin somehow, and the reasoning of well-posed problems, it is reasonable to admit solvable drive space H plus minus 1/2, you know. Is there any idea to connect this?
Not yet. This is not yet finalized the work even under this assumption. So I'm still working, and then try to extend to different settings. But yeah, I assume in some sense I assume a lot of regularity on the kernel in order to get as explicit expressions as I could for the eigenfunctions, and then we can see what can be potentially relaxed.
The point is that this matrix, which is very familiar to Ilya and me,
of course,
there appear an additional decoration which is related to the solvable space connection, say. So these are these Fourier symbols of differential operator, of square root type, say. And I mean, as you work, I think you work in this reasoning, and would be interesting perhaps for you to continue.
Definitely. So in one case, so this is a regular, though not smooth function, but it's the peculiarity of the spectral problem is that it necessarily vanishes. This brings extra detail.
Question, please.
A very small question. Probably I missed in your discussion how do you handle monotonicity of Hilbert transform when you calculate eigenvalues?
how do I show that this is monotonically? It's a trick. It's tricky. So essentially, I compute derivative, and then I try to pass it inside, regularizing it in a sense, and then asymptotically. Well, you can see that. For example, here. So here the dominant part is linear, right? So of course, actually, well, it's dominant because A is there, so and A is large, and inside nothing depends on A.
So the Hilbert transform depends on K and goes to vanishing at infinity, of course.
Hilbert transform directly does not depend on A. It depends on
what?
So it depends on it depends on lambda through K0. It depends on the kernel itself, and then it's yeah. So it's Hilbert transform enters the story is so Hilbert transform of log of this function, and there is no A there.
Okay, we discuss it.
Mm-hmm.
I have to move on, so thanks Dmitry again.